that was another question. Does a small chalk really hurt? In the recent days, the reading of it? No, it didn't.
This is a small enough board that it doesn't seem to matter.
Okay. Set the camera. This is the only room I teach, so setting the camera has become much easier. It doesn't change much. Let's set the legs a little. So we have homework 6 tomorrow. I would have liked to do more examples before the homework, but we went a little slower. I think we are already late by a lecture or so. So whatever examples we do today is going to be your help. And we have lectures from the last year. So we'll stick to this due date. Midterm 2 remains the same, no change. Thursday, 5 p.m. is it? That's what we were talking about. And there will be a midterm 3. Optional. But decide at least, you cannot again decide on the last day or right in the morning of the exam that I'm stressed that I don't want to take it. Let's say 1 week before or 10 days before you decide about the dates, right? Decide, how about that? Decide by midterm 2. Decide by, no, October 31st. Whether you want to take it or not. And I think around midterm, sorry, around November 15th or last Thursday before. Yes, would you prefer Thursday if you're taking? No, let's not discuss this. We'll discuss about it later, right? Last week before Thanksgiving. Is it okay to write Thanksgiving as TG? That I think you guys know better. Or is there anything any offense in that? No. Okay, so that is an open thing. I will decide it within a week or so. And yeah, okay. So that's all, I guess. Yeah. So we were doing contour integrals. Any comments or anything you want to mention before I proceed? Anything on the logistics or the subject matter itself? Anything? Now that today we have a full house. Okay. So this is contour. Integral. It is a direct application of Cauchy's theorem. If you want, remember Cauchy's theorem says that if a function is analytic in a region, and that is of Cauchy's theorem here. So this is you have a function f of z analytic everywhere. Everywhere in that region, that's important. So it's your contour C, it's understood that's a complex plane. Then dz along that contour f of z is equal to 0. That's a simple statement. And then we extended this idea that what if there is a small pole there, And if you go around it, it contributes. So that's one more thing you can say. Okay. So this is Z, Z, F, Z, and Z minus A. So this is called a simple pole when it is of the form 1 over Z kind of structure. That's called a pole. And this comes out to be equal to, you can also put, usually it is called 2 pi I times F of A. Because whatever is F of Z gets replaced with Z equal to A, whatever is the pole. So it seems like it's a very, even if you don't understand the details, it's kind of a prescription. And that's called the residue theorem, and very powerful statement there. And if you remember, it is like a delta function property you study in another context. So the example we were doing was related to causality or a step function. We said, let's talk about the function figure of t. And that's 1, 0. If t was greater than 0, it is equal to 0 if t was less than 0. Okay. But then we said that, oh, if we do this, we have some trouble. It leads to an ambiguity in the definition of the Fourier transform. So we said, oh, let's extend this as a limiting property. So let's say this is limit delta tends to 0 of exponential of minus delta t. 0, and this is for t greater than 0. And it's at least at this stage, it's harmless, right? I mean, it doesn't matter whether it is this or that. It seems like in the limiting condition, it's the same. But in the Fourier transform, this is well defined, but this is not well defined. So Fourier transform of this quantity will be, we said we used a to represent the Fourier transform function for this, and we said this is dt e raised to I omega t. dt omega is minus. And there's a chance that some of you may not have seen Fourier transformations in very detail, but that's part of this course itself. So it's kind of going up and down here. But all of us should have seen it somewhere or the other for sure in an undergraduate level, but not in a very formal way. Yeah. So the Fourier transform of theta of t is defined this way. Substitute this, do this integral, and whatever it comes out is the Fourier transform of. And we showed that this is equal to, so if you were to substitute this, that's the same as minus infinity to plus infinity dt e raised to I omega t and e raised to minus delta t if you want, right? But then this is only for t greater than 0. So t has to be, this is t greater than minus infinity. So this has to be 0. Is that clear what I did? I did a couple of things together. Okay. And this is, if I were to put an I square there, it's omega plus I delta. This is equal to so let's do slowly. E equals to I omega plus I t. Do the integral. That's equal to 1 over I plus I delta. And then you have to evaluate it at infinity, at t equal to infinity. Delta t. At t equal to infinity and at t equal to 0. At t equal to 0, this is all perfectly fine. At t equal to infinity also, earlier if there is this delta is not there, then it is oscillatory. Then we have problems as to where does it end in the oscillations. But if this I delta is there, that makes it I square is -1 and it converges off to 0. Once it converges off to 0, it doesn't matter whether it's oscillating or not, if it's 0. So this becomes well defined. So it's -1 over I plus I delta. That's what we want to keep us. Raise this is equal to -1 over I, 1 over omega. If that is the case, we should be able to Fourier transform this again, and this should give us theta of t, right? And that's the exercise we want to do in the context of contour integrals. Let's now do theta of t. Like this is a cycle, right? We started from here. We found the Fourier transform. If I transform this again, the inverse transform of theta of t, I should get back my theta, the original step function, Heaviside step function, if you want. So this is -infinity to +infinity d omega over 2 pi. And this is e raised to -I omega t. Notice the minus sign here, that's the inverse. In time, this is I here and -I here. If you're doing spatial Fourier transform, it's the opposite. That's a notation, it's not necessary. If you're doing it in mathematics, they won't stick to this. But in physics, time and space behave slightly differently because of the Lorentz transformation. That is a minus sign with the time. So this is negative here, positive there. If you're doing space, like quantum mechanics, for example, position and momentum Fourier transform, that opinion. Again, that's a notation also to a certain extent. That's theta tilde of omega, and that leads to the integral if you want. So there's a 2 pi. If I were to substitute this in here, so that's 1 over 2 pi I. Omega and exponential of -I omega t divided by omega plus I delta. That's the integral we have. This is this integral is it is not very cleanly doable in general. So let's just to motivate that fact. Let us say this exponential was not there. Like suppose you have 1 over omega plus I delta. And if I were to say I want to integrate over this, how does this look like? -infinity to +infinity. This will be, this is equivalent to, if I were to plot 1 over omega, this is omega, and 1 over omega will be like this. So this is 1 over omega. So that's how this function will look like. If I'm integrating over it, suppose, especially if I were to ignore this delta, like because it's the limit delta tends to 0, but that's important that you go in that limit delta tends to 0. This is the area underneath this. The extreme limit when delta goes to 0, only in the extreme limit, what is the integral equal to? If you were to go to -infinity to +infinity, it seems like there is a negative area here, there's a positive area here, that's actually 0, right? But it is going to infinity here, right? There's an extreme infinite quantity there, there's an infinite quantity here, and they cancel out very clearly. And you would say that, okay, what do I do? Then I can put in some small, I'll put a cutoff, right? Here we put a cutoff there. This was an innocent cutoff because it seems all clean, right? But here, if I were to put a cutoff, so this two, then you would say, oh, I have an infinite quantity here. And I have an infinite quantity here. Right? But that subtraction is not well defined. Right? That has to be very, like for example, if I were to take a limit epsilon1 here, epsilon2, if I first do epsilon1 and then do epsilon2, it will be a different answer from epsilon2 first taken, epsilon1 taken second. And even if you put equal, then you say that, oh yeah, then it exactly cancels out. So there are three different arguments you can use. So it's not very obvious what exactly it is. And that's what is showing up here with the function, of course. No? So it is not very obvious as to what has to be done. But this is the stage where we will see that if we go into complex plane, all this will become very clean. This is on a real line. Right? This is omega is real here, even though this quantity is I delta, omega is real. Right? Omega is on a real line. Omega is a real parameter. So how do we, so this is where contour integrals come. This is the basic idea of contour. So let's see how this can be handled in a very clean way using complex analysis. So so instead of doing this as a, so this is what we would like to do. Right? We would like to find out what this is equal to. And of course, we know the answer. We are specifically doing a question which we know the answer so that we can actually check and how things work out. This should give you this answer, especially the two independent answers, right? 1 and 0. How does that work out? So let's, instead of theta of t, let's have a new function. Let's call it g of t. Very quickly, I will call it g1 of t and g2 of t based on whether time is, because there are two answers here, t greater than 0 and t less than 0. So yeah, or let's stick to this right away. So let's say t is greater than 0. And let me call this g1 of t. So that's a function I'm defining, but now this is going to be a complex integral. So this is dz. I want to have the 2 pi I. That is dz, and that is contour c. And I want to keep it as close to that as possible. So that's minus I z t, and this is z plus I delta. I want to check if really the minus sign is there or not. Yeah, so there is a minus sign also in there. Minus sign. And since there is a delta, I should define that also. So this is all limit delta tends to 0. And then it means from which direction, right? From the positive direction. If delta is a positive number and it approaches 0. It will matter that if you change it, and we will see how it changes. But once I specify these things, this is some function. And the immediate question comes, why did I write this? Why not any other function? And that's the biggest challenge in contour integrals. That how do you come up with the integral that will help you evaluate this? You will see why these two are connected. In fact, this two seems almost a rewriting of omega to z there. But that's not always the case. We will do examples where that's not the case. It has to do with the contour, and you will see this in a minute. Okay, and now I have to specify the contour C, and if it is a closed integral, then we can use Cauchy's theorem there. And so what is Cauchy's theorem? Cauchy's theorem says that if it is an analytic function, it is equal to 0. Is this analytic? Is the integrand analytic everywhere on the complex plane? Right, Johnny? Yeah. No, right? And why not? Yes, that's correct answer.
It will include that there is z plus I delta.
Yes, so this goes to 0, right?
Yeah.
Somewhere here, denominator, then it goes to 0, it will going to blow up. So there's one point where it is not analytic, other than infinite regions are the real. So let's clarify that. So that is, this is the complex plane in Z now. And when Z is equal to minus I delta, right? When Z is equal to minus I delta, it will be somewhere here. That's minus I delta. Right. Whenever Z is equal to minus I delta, that's equal to 0, and that blows up. So you don't, if you have a contour that encircles this, then there will be a residue. If it doesn't encircle that, it's 0. Right. So that's so so now we have to choose a contour. So let's say t greater than 0, right? I want to do t greater than 0. Oh, let's do t less than 0 first. Just because there's one feature that is, let's do a simple one before the harder one. Okay. So at this point, I can choose any contour. I have not specified the contour C here, right? So in that sense, G1T is not specified yet. So I say that, and this is again from experience, it comes that which one I choose. And let's choose this to be going along the real line, and then come back in this manner. So there is a circle I have defined here. Let's say this circle is radius r. And this is on the horizontal or the x-axis. And I want to specify like C is, let's say this is C1 and this is C2, and we mean R goes to infinity. So in that way, there is not only delta going to 0 plus, there is R going to infinity. Okay. So this is now more specifically. This is limit delta tends to 0 plus, limit R tends to infinity minus 1 over 2 pi I. This is now C1 plus C2. That's it. Z. Is that clear? And that's the contour. And it actually goes all the way to infinity, and that is necessary because this is R, right? Plus R. My goal is that when I go on the x-axis here, that's actually exactly my old integral. That's the integral I'm interested in evaluating. Like that's the point, but for now, that's what it is. Any questions at this stage, at the steps I have already done? But before we proceed, what is this equal to? Equal to? This is G1T, yeah. Yeah, no, that's correct. But what is this equal to using Cauchy's theorem?
0.
It's 0, right? Because if it is analytic everywhere, that's first one, then it is 0. And it is analytic everywhere in this because it is not analytic at one point, but that is outside the contour. So I don't worry about it. Right? So it is equal to 0. Right? So that's so what I can do. So using Cauchy's theorem, the G1 of T is equal to 0 using Cauchy's theorem. If G1T is equal to 0, this involves two contours, C1 plus C2. So the integral on C1 plus integral on C2 is equal to 0, which means integral of C1 is minus of integral of C2. And that's the key. Okay, so you choose a contour which you know the answer, even if it is not 0, it might be a residue. But this consists of 2 pieces. I can know information of one by integrating on another contour. Like it might be hard to do this integral, but it might be easy to do the other one. That's the key. Okay, based on one, it's like earlier I said, analytic function has this property that somewhere else decides what is happening here. So it may be hard to do it here, but then go somewhere else and do the integral, and it might be the same if you can get such a rule. So here, because of this, we can say that limit L tends to 0 plus limit R tends to infinity minus 2 pi I C1 of dz is minus IZT z plus I delta is equal to minus of this. So this is limit plus 2 pi I. Change the I can change the camera. So this is minus IZT. Okay. Let's stick to C1 now. Okay. Any questions at this stage? Maybe the overall bird's eye view is still not there because why we are doing each step might be off a little, but a few steps you understand. Yes.
So we chose 2 contours here. Is there any, is that kind of like a limiting factor?
No,
By
it
making
could
a
be,
statement?
no, it could be often, sometimes you do this kind of contour. So you can go this way. Is that your question?
Oh, yeah, okay.
That's possible contour. Sometimes you even do, like all fancy contours are possible, whatever is convenient.
Okay.
Doesn't have to be on the x-axis, it can be anywhere.
I understand.
As far as the idea here is to get the information about one part using another part. If one part is tough, second part might be. If both are hard, you're stuck. Right? Yeah. So that's the trick. That's the only trick I know. Okay. So now how do we see how is this useful? Let's see. Now I'm going to actually evaluate this. Okay? All this was formal statements. Now I'm actually going to evaluate this. Let's start with C1. Right? But C1 I cannot evaluate because it's going to be the unknown, right? So on C1, that's on the real line. Right? It's only my x that changes. Y is fixed on the real line. So on C1, let me substitute z as x plus I0, right? Because y is 0 there. Like on C1, that's what it is. So I'm basically substituting dx is equal to x. Right? So dz is equal to dx. So put it in here on the left hand side, or let's do left hand side if you don't mind if I use this. Is this common? I don't see it is very common here. Yeah, it is common. Okay, left hand side, right? So that's my contour C1. Let's limit delta tends to 0 plus limit R tends to infinity, and this is minus 2 pi I. Okay, on C1, I'm going from this point to that point. That's minus R to plus R. That's minus R plus R. That's my limit. From here to there. And I'm going along the x-axis, and dz is dx now. And z everywhere I put as x. And this is x plus I delta. that clear? The r going to infinity doesn't seem to hurt this integral at all. So you can as well take this minus infinity to plus infinity all the way. And then you will see that that's exactly theta of t. Like omega can be thought of as x. So this is your theta of t. You recognize that this is theta of t. I have not specifically written delta tends to 0, but that was understood there, right? It is delta tends to 0 is there. So that's exactly theta of t. No ambiguity at all. It's very clear. And we argue that, oh, that's not a very well-defined integral, or it doesn't seem to be a well-defined integral on the face value because, oh, there is a cancellation of infinities coming in. But we will see that it is actually well-defined because of this delta. Okay, clear? So that's my theta of t then. So that's theta of t. Which means that if I can evaluate the right side, I have done my integral without actually doing the integral. I'll do it using Cauchy's. If Cauchy is right, then this must be correct. Okay. So now let's say on C2 then. If you have to do the right hand side on C2, again I have to make a substitution on C2, right? Usually this is a line integral. On a line integral, there is only one parameter. Like z is not a very convenient parameter on a line integral because there are two variables on that. So we want a better variable, and we notice that angle theta is probably better on a circle. Right? Keep the r fixed and theta as a changing variable. So then the substitution will be z is equal to r e raised to I theta. Right? That was one of the Argand diagram representation of a complex number. So that's perfectly fine. R cosine theta and R sine theta, right? So R e raised to I theta, and that's it. And then I do the same thing, and R is fixed, notice, right? And on that contour, so I don't have to change the. When I take the derivative dz, this is only the theta is changing on the contour C2. So this is I R e raised to I theta. Again, do the integral. So now we are doing right hand side of that statement, right? You write limit that is plus 2 pi I now. Now the limit is going in the angle, right? So angle is down here. So that's your angle here. Because r cosine theta then is x and r sine theta is y. And along the contour C2, angle theta is going from 0 to pi. Right? So this is this integral, because I made that substitution, this is going from 0 to pi. dz now is I r e raised to I theta. Exponential minus I t, z is r e raised to I t. It's an exponential in the exponential. It seems like it's going to be very hard, but let's see how all this works out. Divided by z plus I delta. Z is r e raised to I theta plus I delta. Any questions on algebra or in general? Any questions? Currently, I just gave it. There's one way of doing it, but then it seems to be an overwhelming expression. Clear? But yes, it is. If I were to ask you to do this exactly, that's probably not possible as an integral. But it's all done in r tends to infinity. Right? In that extreme limit, this has a very simple expression. Okay, so let's think of this integral in that extreme limit. So let me go to the other code. This is 0. There is an I, so that I cancel with this I, by the way. So I and an I can cancel that. Right. And there is all e raised to I theta, d theta. And in the denominator, notice what is happening. This is a exponential of I theta. What's the maximum value it can take? Exponential of I theta. 1, right? Cosine theta plus I sine theta. This is an oscillatory function. It cannot go beyond 1, not less than 1. R is huge. Right? And I delta is very small. Right? So this is going to dominate. This is very dominant. So in principle, I can do it right away, but I'll do it in the next step. Same thing happens in the numerator. This is an oscillatory function of an oscillatory function. Right? So let's do that carefully. So so here I say e raised to minus it, or e raised to I theta, I say is r cosine theta. And then there is a r sine theta, right? I r sine theta. So it's e raised to I t r sine theta. Is it clear what I did? So I just expanded this exponential. And the denominator, I take out the bigger expression. Just to write it as 1 plus I delta over r e raised to theta. Just dressing it up in a sense to argue, make the arguments. Like I could have done that here itself.
Would the I in the second term of the, when you expanded the X,
Mistake. Plus. Right, that's what you say. There is an I there, minus I plus 1, because exponential I theta r sine theta plus I r sine theta. I multiply that with minus I, right? The minus it, minus it, minus it, so that's minus it r cosine theta, minus I plus I, this is plus r, there's a t. Oh, did I mess up? No, sorry. Sine theta. Yes, sorry. Hopefully that didn't confuse. So that's that plus. Okay. Any questions on that? Each piece, how that comes algebraically? Okay, if that's the case, if we reach there, now we take the limit r tends to infinity as much as we can. This is small, that's large. This is 1. This is going to be really tiny. So this is going to be negligible. And down here, notice, what can you say about this exponential? This is not an oscillatory function. Sine is oscillatory, but exponential is not. This is an oscillatory function. Right? This is plus tr sine theta, sine of theta, but theta is between 0 and pi. Correct. So that's positive. So let me think of exponential of t r sine theta. This is positive. This is greater than 0 because theta is between 0 and pi. Right? R is the radius of a circle. That's also greater than 0. T, we started with the statement that we are going to work for T less than 0. Right? So this is less. So this is less than 0. Oops. Minus and a positive quantity, that's a negative quantity. And a very large negative quantity because R is going to infinity. Exponential of a very large negative quantity is. So this is something like exponential minus R, some constant, some greater than 0. Right? What is that equal to? The limit R tends to 0.
1.
Sorry, R tends to infinity. No. If exponential goes away, right? Like exponential of negative, I think I said R tends to 0, R tends to infinity, right? I think I said R tends to 0, my fault. So the limit R tends to infinity, it goes to 0, right? Exponential really suppresses it. If it was positive, then it would blow up. Either the exponential blows up or it goes to 0. Right? So this goes to 0. Clear? So this basically goes to 0. This is 1, and there is an R in front, but this R cancel out. That's very crucial. Unless that R cancels out, that would have contributed. If it was any other power, that cancellation would not happen. If it was Z square, for example, that would not happen. And only for Z, it works out this way. And so notice a lot of arguments went through that this exponential really was needed. Like how that angle, so if I had chosen the contour on the bottom part, for example, it wouldn't have worked. Only from theta equal to 0. I could have had any cone there and I could have worked that way. So that's, so this is going to 0, this is 1, these two contributes. So this is basically 0. Okay, because the exponential basically tells that if you want, you can write it in a more slightly better way, that you can say this is limit delta 1/2 pi times 0 to pi d theta times e raised to minus I t or cosine theta, and that is exponential of minus basically t r sine theta. But this goes to 0, so the whole thing goes to 0. All these arguments that I talked about just now, like in the limit R tends to infinity, this thing goes to 0. That's called the Jordan's lemma. It basically generalizes the whole thing. I did it for a very specific scenario here. If you do this in a more general way, you can write it as a theorem that whenever this happens, if you're in the top half plane of the complex plane, then you can actually make it go to 0. Okay. So what we have done then is the right hand side is 0, the left hand side was theta of t. So we have shown that for t less than 0, t of t, this Heaviside step function is actually 0. Like we have done half of our. Okay. And one might think, like, since you're really doing this for the first time, you might think, oh, all this seems to be fishy. It's not very convincing, but you can go through that argument very carefully, and they're all clean, perfect arguments. Like there is no catch and all that. There is no, or most importantly, there is nowhere where you're subtracting infinity. Like it's all, if Cauchy's theorem is well defined, that's perfectly okay. And Cauchy's theorem, we said, is perfectly okay. So in that sense, this is equal to 0. So now let's do t greater than 0, and let's try to repeat the whole thing. So now let's say t greater than 0. And again, I have to start with the contour. So this time, let's say we choose our integral to be. So the limit delta tends to 0 positive again, minus 2 pi I. I will start a new function with a new, the integrand I will keep it same, minus I z t, z plus I delta. But I'll go on a new contour now. And simply because I go on a new contour, C prime, let's say, that's a new function then. If I evaluate something on one contour and on another contour, those are two different functions. Even if the integrand is the same, it's like saying limit of 0 to 1 is not the same as the integral of 1 to 2. Like, or integral going from 0 to 1 is not the same as integral from 1 to 2. So I say this is a new function. So this is, I call it G2. And the primary difference, I say, is, so this is again that Z from minus I delta. This is very scaled out or zoomed out picture. This is supposed to be very close in the limit delta tends to 0. And remember, the contour C has to be always, if we want to use Cauchy's theorem, you should remember that this that Cauchy's theorem requires it to be counterclockwise, right? Counterclockwise, and we can actually define G2T as any way we want to. But if whenever we are using the Cauchy's theorem, we should make sure that it is in that same. So, but I'm going to use it clockwise. Just well, one more thing that I want the x-axis to align with my integral theta of t, right? As close as possible. So for that reason, that's my integral there. To have that insight there, I'll go clockwise. It is, we should remember that Cauchy's theorem is the opposite. So whenever I use Cauchy's theorem, I should, and this time I go this way. And why that way? Because now I would this is t is greater than 0, but theta, then I can choose it to be negative. I'll again get the same exponential. If this is positive, then it will explode. And I don't want that, because then I'm stuck with the same infinities. I want to avoid infinity. I'm staying away from infinity. So I'm using this. And again, let's call this C1 and C2. Or let's say C1 prime and C prime. Okay. And let's again say, using Cauchy's theorem, what is G2T? What is it equal to? Well, let's begin by saying, is it 0? It's not 0 because there's a pole now, right? It's really not analytic everywhere. But then this is a simple pole. So we can use the residue theorem and say that it is 2 pi I. But before that, this is in the wrong sense, right? So minus 1 because it's the wrong sense of the contour, right? So direction of contour. So that's important. And then there is a 2 pi I. And then a residue, whatever is the integrand, evaluate it at z equal to I delta. Right? So I have to, whatever is the integrand, which is minus 2 pi I, exponential of minus I z t. Forget the denominator, right? We don't worry about the denominator when we are taking the residue. This has to be evaluated at z equal to minus I delta. Is that clear? When we say f of a, right? That's what we are doing. F of a is everything other than the z plus I delta. Is that clear what I did there? No. So let me.
Why there is another 2 pi after the minus?
Because that's also part of the integral, right? Remember dz f of z over z plus a or z minus a, right, was 2 pi I times f of a. If there is a constant here, say 36, and this is 36. Correct. So that 2 pi I is there in front, that will contribute to that. Right. So that's exactly what I did. You ignore the z minus a, the denominator, the simple pole, and we write that's you, and there's a minus sign from the direction of the function. Okay, clear? Okay, so now we can do this. 2 pi I cancel, minus 1 cancels, and when z is equal to minus I delta, this is how much? Minus it's e raised to minus delta t. But we had this delta tends to 0, so that's equal to 1. Which is the same as what we had here, right? This was exponential minus delta t, and we reached 1 from this to 1. So we're going by opposite. So we know G2T now, right? Clear how we used that, but that's not what we are interested in. That's G2. That's an unknown function we are evaluating. Our idea is to get theta 2, but our goal is that, oh, on this contour, that's nothing but theta 2 of the heavy strike step function. So this plus this is equal to 1. So this will be equal to 1 minus of this. So let's do that. So let's so integral of C1, if I use this shorthand notation, C2 prime is equal to 1. Okay. Is that clear what I mean there? So this means, let me just write clearly. Okay. Limit delta tends to 0 plus minus 1 over 2 pi I. C1 prime, the exponential minus C. Earlier it was 0 in the other function T1T that we clear.
Yes.
Again, do the same thing. There are 2 pieces there. Oh, so I'm interested in this, correct? So C1, let's say. C1 prime. On C1 prime, again, the same idea. I'm going from left to the right. So Z is equal to X, right? Or omega, you can say. dz is equal to dx. And the limit goes from minus r to plus r. And here also, let's say the radius is r. Right? And it's the radius is still positive, right? Positive. So limit goes from minus infinity to plus infinity. On C2 prime, let me do this together. C2 prime, I substitute C is equal to R e raised to I theta. Right. C2 is going from 0 to minus pi now, if you want. Or if you were to write it as minus, it is going from pi to 2 pi, either way you want to think of it. So that's then dz equal to I R e raised to I theta. Okay, so doing this together, so we have limit delta into 0 plus r going to infinity minus 1 over t cos I. C1 is dx now, going from minus r of r and e raised to minus I x t cos I. That's the same theta of t, and this is of 1 minus. Okay. Now C2 prime goes from 0 to minus pi. That's the difference. We're going, and it respects the contour also, right? So clockwise contour. We have used the counterclockwise in the using the Cauchy's theorem. dz is IR e raised to I theta e raised to minus IT or cosine theta, that is e raised to t or theta. Pretty much the same, but the angle theta is, the contour is in a different region. That's the main. Otherwise, as far as algebraic expression goes, it's pretty much the same. And that's it, all equal to 1. Okay. Questions? Yes.
Your choice of direction for the contour, how was that like, how did you make the choice of clockwise?
It doesn't matter. My main idea was that C1 prime should give me my old integral. If I were to choose, let us say that I chose it the opposite sense, right? C1, so this is going counterclockwise. So what will happen is that at this point, when I'm identifying my integral, that will go from minus x to plus infinity. Right? This will be minus infinity to plus infinity. It will go from plus infinity to minus infinity.
It shows up in the integral.
Correct. Yeah, it shows up in the integral. This one will again be from now minus pi to 0, again in the opposite sense. And this will come out, you will lose this minus sign, so this will be a minus 1. It's like overall come multiplying by minus sign. That doesn't matter. Yeah, it should not matter. And again, you could do this for any contour. For example, even though this is the simplest contour, you would say that, no, I want to do this actually for this contour, some complicated contour. If you can actually do all the other pieces, it should give you the right answer. In fact, if you cannot do it and only one piece is missing, it better be this, right? So it's a, once it's an identity, even if you cannot do it and it's only one piece missing, then you have a new result. Right? That's the power of this. If you can do all other pieces, one piece remaining, you know that has to be true. Yes.
So extending R to infinity was a crucial point.
Correct. Correct. Exactly.
Okay.
Exactly.
Because it's not just obvious that'll happen at first. So
Yeah, exactly. And that's why this played an important role. I mean, it's yeah.
okay.
And it's also the fact that, remember, at infinity, your function is not analytic, right? So that's at infinity, exponential function diverges. So in that limit, it's okay. It's the same idea as you get closer and closer to the pole, it's growing to infinity. But as far as you don't sit on it, you're okay. It's like going close to the charge. Yeah. So it's very fine balancing act here. But And in the beginning, it may not be convincing, but you can try to find a loophole in this, and there's no loophole. So this is theoretically perfect. That's the point that I'm trying to tell you, but you will have to go and really question that. Until then, it's just a statement you have. But this is completely foolproof. There is no subtraction of infinities. And this is the sense, I mean, this is the right time to say it. I mean, probably you have seen this result, 1 plus 2 plus 3 plus 1. What is that equal to? Any chance? Anyone knows?
1/12.
Yeah, minus 1.
Oh, yeah, minus 1.
Right? Minus is important with the success. Add up all these positive quantities and you come up with this negative number. Okay, not only negative number less than 1. So seems like meaningless. Like this is, come on, like you add up all these numbers and you get a minus 12. And then everyone will say, no, this is true. This is really correct, right? And that is in this sense, like it doesn't mean adding 1 plus 2 plus 3 at all. First, you take this to a function called Riemann zeta function, right? And that function has a lot of properties. At that real point, it is infinity. And that's this left-hand side. But if you approach it, that's where it approaches. And it's very well defined. I mean, if you plot it, it is actually blowing up. But in that contour limit, this comes out perfectly fine. And that's the sense in which they're saying that this curve. So it's a very well-defined quantity, but it should be understood in what sense it has been evaluated. So that's a function that doesn't exist at that point. So left-hand side is, in a sense, saying it's naively said that this is equal to this. So what is correct is that Riemann zeta function, this will be 1 plus 2. So I think this is Riemann zeta function of 1 or minus 1. Riemann zeta function evaluated at minus 1 is equal to 1. The outer equality is true. To say that this is equal to this, that's a loose statement. Like they mean it when they say that, but that's a loose statement. That's just for convenience. It is okay, but that's not true. But this is true, perfectly true, well defined function. So, okay, that's just a popular statement. Okay, so coming back to this, so this is theta function, step function, and step function, theta of t for t greater than 0 now, right? And that's equal to 1 minus of 1 minus of this becomes plus. So this is we do the same thing, 0 to minus pi. So I cancels out. So r e raised to theta. Theta. Let me pull out that r denominator also. Same arguments. Exponential minus I t or cosine theta. This is okay because these are oscillatory. There is no infinities there. So this is e raised to t r sine theta. It looks structurally the same. Comes to infinity. If this balances, like these r has to cancel out. Only after that, that whole thing goes to 0. If this r by any chance did not cancel out, if there was an r square, for example, which would have happened when z square is there in the denominator, then no, not even z square, even z raised to 1.1, it will blow up. Right? So this is again 0, so that's equal to 1. And good. So that's all we need, and that's here. Well, I would have liked to do more examples, but this is the arguments you have to use to go through. And I wanted to go slow purposefully so that all the fine arguments are there. But these are the basic arguments. Every contour integral goes through these arguments. main thing is the splitting. Unless you see more examples, you don't see where other contours are. It seems like a contour was very simple here, but that played a crucial role. And then splitting it in the right manner. Yes.
So now can you make the full statement that the whole circle is just one? You can add to both G1. and-
Yeah, but that is not useful for you.
Right.
Yeah, that's okay. Yes, the whole circle is, so your statement is that this whole statement, like this contour, C,
Yeah, all space.
C, right? So let's say C plus C prime here, right?
Mhm.
Right, or let's say C3, right? C double prime. You're saying dz e raised to minus I z t over z plus I delta on that is equal. Yeah, it's not 0, right?
No, it's equal to 1.
It's equal to
Yeah.
1. Yes, that's correct. Yeah.
And that's all space, right? That's
That all stays. Yeah. So this is also true, but this is not very useful. Right? This tells you that this integral plus this integral is equal to 1. Which is a little, hold on, isn't it a little worrying here that because this is 0, correct? Separately?
Mhm.
Well, is there? Yes, because that was this, right? C2 prime is 0, but that's equal, sum is 1. Okay.
Because it's not analytic on the bottom.
Oh, yeah. Yeah, correct, because it's not analytic. Yeah. I was confused. Yeah, so this works now, right? Yeah, this is perfect because, and yeah, I was confused. You guys probably had. Yeah, very good. Thank you. Yeah. So it's all consistent. Yes. So this is also correct. So if you are interested in this integral by any chance, if you want an integral of that kind, then you have an answer.
I like the all space. I don't know. It's cool that you can extend it to all space. I guess it's like the reasoning.
Correct.
Instead of,
Correct.
yeah. And so you can have more than one point that's non-analytic. Like
Yes,
we can
yes.
go ahead and put 2
Yes,
points.
so the classic example, I think in your homework, what you see is this example. Z square plus A square.
Right.
Right, so now there's a minus and a 2 or 1. If it is Z square minus A square, it's a little sensitive because now you're on the real line, right? And if you're on the real line, the challenge is that when you take, if your integral is going through the real line, you're crossing the pole. And the pole, remember, is infinity there. Okay, I mean, it's just one point, but it's not okay. So, but if you, and often you will see in literature, okay, I'm going to go this way then. Okay, you will see, but then it's no more the integral. That's no more your original integral. So be careful on what you're concluding. This is correct. If you go up and down, so there are lots of contours you will pick and you can get answers. But that's no more your original integral. Your original integral is supposed to be on the real line. Even a tiny shift. Typically, tiny shifts are harmless, but this is not a tiny shift, any kind of tiny shift. This is an infinite. You're going around an infinite. You have to be careful. But best you can say is that, okay, this is contributing to it.
Could you have gone all the way around? Like
Yeah, but then your integral was to go from here to here, right? It has to cross that. Right? So you're stuck there. So typically what you do is, so here is, so to avoid that, what you would do is you will go back to your integral here and shift this right there plus I delta. Like here, what I did was, see, all this was very cleanly done in a sense. I changed the integral there. It seems very innocent here. Oh, how can this be wrong, right? But that delta was very crucial to shift this down. It was on the line. If I don't make that shift, it is on the line. And I don't know how to do that. That's undefined. I don't know how I interpret that. So I had to go back somewhere where it makes sense, then do the shift. Oh, then it is okay. And then you would say that why should be delta greater than 0? So you come back and say that oh, delta is less than 0. And you can do that again. So for example, it will be my For me, it is very easy now that I've gone so slowly here that in an exam I can ask, what if delta was, so here if somewhere delta is 0 plus, right? What if it was 0 minus? How will it change? Right here, this delta is 0 plus, that's necessary. Here it seems like it is innocent. What is it? Okay. And it is different. So it's very special function, very one way it comes this way, it's another way it's something else. But it's clean. There are a lot of restrictions, it's clean.
So choosing these contour paths are like,
Yes, exactly. Yeah. And you can do classic problems, like there is this, I think the favorite I know is the most complicated one that was done is Sommerfeld. So if you are doing a scattering problem of a half plate, like diffraction from a pinhole, these are classic examples of pinhole or just a disk. These are all examples people used to solve in 19th century, like 1850s and all, after Maxwell. So it's very common. And then one is that you have an electric field coming in. So this is a wave, and this is a half plate. So basically a conductor. Right? And what is a scattering or diffraction pattern on a screen here? And it was very hard to do this problem, but Sommerfeld, using complex integrals, solved it exactly, no approximation, an exact manner solved. And again, it is elegant because you're not really solving the problem, you're actually solving some other elementary problem, right? The idea is to connect the two using Cauchy's theorem. You're using some standard result to get some non-standard. Like in physics, you would say like black hole, right? Or our edge of the universe. It's very hard to talk about the edge of the universe. But we can say something about the edge of the universe if we assume that everything is like, or if we can assume this complex analyticity, whatever in physics it means, if that connection can be made. And in this context, yeah, one more minute. I think I mentioned it in the last class, refractive index. Right, refractive index. Your refractive index is a function of frequency, which we know is color dependent, by red color or blue color. There is a real part to this, and there is an imaginary part to this. That's your U and V if you want. Right? And using these, you can say this has something. This is the real part. Typically contributes to the refractive index that we know and that we use in introductory physics. And this is the absorption coefficient. This is related to the absorption coefficient, right? How much energy you lose in the material. And using these contours, you can, and this is a statement, very strong statement you make, that the reflection is actually decided by absorption, which makes sense in the conservation theorem, right? I mean, if a material is absorbing something, whatever is remaining, it must be reflecting, and that is a transmission also. So it gets connected with conservation of energy statement. So absorption is completely determined by reflection. In fact, in experiments, you would not do the absorption part, you do the reflection part, and then you conclude something about the absorption part, because one is harder to do. So it has gone to the stage where it is trusted extremely well. And if there is some flaw in that, then you look for, oh, where is this all going? Yeah, I should stop. Good, hopefully this will. You're not taking the class, right?